hypothesis testing. I would like to brief about our today's resource person, Dr. G. Balasandri Kumar. He is now presently serving as a professor and head of Department of Business Studies in the School of Arts and Science in Sri Manakula Vinayakar Engineering College, Pondicherry. Dr. G. Balasandri Kumar has about 20 plus years of experience in research, training, and teaching. He has bachelor's degree in computer science and engineering from University of Madras and MBA from Anna University. He also holds a MPhil degree in management and MSc in psychology. In addition, he has a master's of technology in computer science and engineering and PhD in management. He is currently working on postdoctoral research in the area of digital behavior. His area of specialization includes entrepreneurship, digital marketing, marketing analytics, and business analytics. His professional affiliations are with ISTE, ISTD, NIPM, MMA, IAA, and IAENG. Dr. Balasandri Kumar had written books on operations management, supply chain management, human resource management, and managing technology and innovation in teaching and learning. Currently, he is working on books related to digital marketing and business analytics. He had presented research papers in 53 national and international seminars and conferences. He had participated in 160 plus seminars, workshops, and FDPs, and also published 31 research papers in peer-reviewed and referred journals. He conducts FDPs and workshops on data analytics, business analytics, digital marketing, and startups. So we are eager to listen to your presentation on hypothesis testing, and you can take over the session now, sir.
Thank you so much, ma'am, for introducing. Hope I am audible. So we are on the 6th day of 7 days research methodology for social sciences. I'm happy to present before you the continuation of hypothesis testing that was done in the earlier session, the session 5. So today our topic of discussion will be related to the hypothesis, level of significance, the certain basic concepts which we need to have an understanding on testing of hypothesis. The next we'll discuss on the parametric and non-parametric test, and we'll also discuss on descriptive statistics and how it differs from inferential statistics. And we'll discuss mostly on what are the commonly used statistical tools. And the last one is related to statistics test selection. So before we understand, we need to have a strong clarity on different variables, that is metric and categorical variables. I think that we have earlierly covered. And today we will discuss in continuation with the previous session. Let me just give an overview about what is hypothesis and how hypothesis should be. So hypothesis in a common man language, it is an assumption. Okay, so before we do anything, what we do is we assume things, and we pursue things. When we even look at things, consider that you're visiting a new place and you look onto the weather and you will initially have some perception. So technically, statistically, we call that as hypothesis. So either it can be proved or it can be disproved. It depends on how we experience with things. So experiencing things is what here statistically we call it as usage of statistical tools. So it is based on the combination of variables, and based on the combination of variables, we choose statistical tools and we apply and find the result. And it depends on the domain of study, whether it is commerce or management or business or social science, any discipline in social sciences, it is the same. So how a hypothesis should be? Okay, it is very simple, a very simple sentence, not complex or composite or something like that. So it is a simple statement which declares. It is a declarative form of statement. You say that I feel the climate is good. Okay, I feel the students are able to understand. So it is something like a declarative statement, a preassumed statements. And of course, those statements are measurable and quantifiable. So it is easily measured, though it is a simple sentence, it is easily measurable and it can be quantified. must be knowing now, right? Even the emotions are measurable now and it is quantifiable. Earlier now we don't deal too much with qualitative. You must be knowing like past no from the past 7 8 years, there is lot of emotions being measured through a lot of now we have artificial intelligence into research. This really helps us to even measure the emotional kind. Okay, and it is essentially a conjectural statement. It means that a connective statement. Okay, so basically it also tells you about a kind of a relationship when we deal with multivariate or bivariate things. It also deals with relationships. So mostly, we divide, or two kinds we can say. One is descriptive hypothesis and another one is relational hypothesis. So when we look on to descriptive hypothesis, again, no, it is a simple statement which talks about the magnitude, the trend, or behavior of a population under study. Okay. So it generally talks about the population. Okay, you say that the employees are satisfied. You say the consumers using that particular product are feeling good about that product. So it is no, there is no kind. It is general. No, a declarative statement where it says it describes, that is what it is, a descriptive hypothesis. It describes about the population. So this description might include the magnitude, trend, or behavior. So this is particularly related to the population under study. Okay, so I have put in a very simple example here. All the participants will be able to understand and follow the lecture. I hope you'll be able to understand and follow the lecture. Okay, so this is just an assumption about the population under study. The next one is a relational hypothesis. So when we talk about relational hypothesis, the name itself says that there is a relationship. So when we deal with no bivariable or multivariate things, okay, so we say that whether there is any relationship between this and that. Okay, so whether a climate has an impact on stock market, if I am able to find that, that is also there. So here for an example, I put the participants' ability to understand or follow the lecture depends upon their keenness to learn. So might be they'll be able to understand because they have a certain learning attitude, or their involvement also understands. And this can also be in a different form, where I have taken another variable called as the facilitator's teaching style. Okay, participants will be able to understand or follow the lecture depends on the facilitator or teaching style. So this shows that if the teacher are so enthusiastic and motivating, then the lecture will be easy for the participants to understand. So here, two things are there. You can say two variables are there. One variable is about students' ability to understand or follow. Okay, whether they are able, whether they are happy with, whether they are, whether they are able to understand things what we talk here. And the another one is the another variable is keenness to learn. So whether they are where involvement, where learning involvement is one variable. In the second example, when you look onto the second example, this is one thing, like participants' ability to understand is one variable, and another variable is facilitator's teaching style. So if the people are able to understand, so this talks about, particularly when you look onto the relational hypothesis, this talks about the relationship. Okay, so two things happen. So mostly in no in most of the studies, when we look no researches, that is basically we use only this kind, what we call it as relational hypothesis. Most of the time we use that. Okay. So the next concept, so we initially have some initial assumptions. So coming to the statistical point of view, earlier it was that hypothesis, what kind of a hypothesis it can be, but statistically we usually assume things first, initial assumptions which says that there is no difference between two things, or there is no difference among things that population or the units under study or population under study. So the initial assumptions, we call it as a null hypothesis. The other point which is just opposite to null hypothesis, what we call it as a alternate hypothesis, which is just opposite to your initial assumption. So this null hypothesis can be either a descriptive type, it can be a descriptive type or a relational type. Okay, so this hypothesis can be a relational type or a descriptive type. So initially, no, this talks about there is no significant difference between two things. So here is an example. Okay, here is an example, no, which is univariate, which says that the null hypothesis states that the mean is equal to 3. So we assume that the mean is equal to 3. So we assume that the population mean, hope you must be knowing, like mu is the population mean, it is represented by mu. The population mean is represented by mu, and we have an assumption saying that the mean will be equal to 3. This is just an example. Okay. So what I need to do is I need to either prove this or disprove this. That's it. Okay, so that is what we call it as null hypothesis. Okay, so this is basically, when we look onto one variable. Okay, so consider that there are 1,000 people. Okay, there are 1,000 values are there. I'm picking some 500 values, and in that 500 values I have one mean. Okay, so that mean is what we call it as a sample mean. Okay, and you say that the population with that, looking onto the sample mean, you assume that the population mean could be the same. Okay, so that is an initial assumption. So that is what we call it as a null hypothesis. The next one is alternate hypothesis, which is just opposite to null hypothesis. Okay, so here we say that mu is not equal to 3. What does it mean? It means that it is just opposite, and you say that no. So whenever I'm able to prove or disprove things, consider that I'm proving that my null hypothesis is right or true. Automatically, it says that alternate hypothesis is wrong or it is false. Okay, that is how it goes. So to statistically um, represent this in the form of a graph. Okay, we always say that any kind of a sample distribution follows a normal distribution. Let's assume that it follows a normal distribution. So we have a curve here, a bell-shaped curve, which is a normal curve, and we assume we say that this mu is 3, which is at the center, okay, which is at the center of things. Okay, so here x bar, which denotes the sample mean. Okay. The next one is, so how after applying, consider that I am applying some tools. Okay, I am applying, consider that it is basic thing, I am applying some one sample t-test. Okay, and then next thing is I need to find, okay, at what point of research I can accept or reject the null hypothesis. Okay, so I have an assumption, say that it is 5%. Okay, I say that 5% level of significance. What is meant by level of significance? Okay, what is meant by level of significance? This is how it goes. It says that critical probability in choosing between the null hypothesis and alternate hypothesis. So you choose whether null hypothesis correct or an alternate hypothesis correct. Okay. So this is this depends on the confidence level. Okay. So what is this confidence level is? This confidence level talks about the confidence level of the researcher. Okay, so consider that the researcher, he says that, sir, I am 90% confidence. I am 90% confident about my research. Okay, then what does it mean is that 10% is left out. It means that you are allowing 10% of error. Okay, you are allowing 10% of error. Okay, so this is what is called as level of significance. Okay, so when a researcher says it is 90% level of confidence, he says that he is 90% confidence about his findings about the research, then you can say that there is an allowable error of 10%. Okay, so this is what we call it a significance level. Consider that researcher says, no, sir, I am 99%. Okay, I am 99% confident. Then it means that you are allowing 1% of error. So it means that it depends on the confidence level of the researcher. We determine the significance level. So generally, what we do is in social science, most of the social science research, we typically choose the level between 5% and 1%. This is the level of significance that we usually use, probably 5% error or 1% of allowable error, which we call it as the level of significance. Okay. So if I say it is 95 percentage confidence of a researcher. So if the researcher is confident about 95%, I mean that it is 5%. So in terms of probability, I say that it is 0.05. That is what is written here, 0.05. If it is 1% level of significance, I say that it is 0.1. Okay, so that is how it is determined. Okay, so looking on to the graph which we have seen just now about how we are going to do it. Okay, so consider that a researcher is no, saying that he is 95 percentage confident. It means that it is confident level. Okay, consider that if it is 5 percentage, it means what does it this 5 percentage tells you? It is the level of significance. So level of significance is 5 percentage. Okay, you must be knowing that the normal curve has both a side. You have a left side and a right side. So this is left side and right side. Okay, so if the whole 5 percentage, if the whole 5 percentage is taken here, usually the rejection area will be this side, okay, or the rejection area will be this side. So both side. Consider that you are choosing both the side as a rejection area. It means that you say that it is 2.5 percentage here. You are going to reject on the right side, and on the left side you are going to reject 2.5. So totally it is 5 percentage. Okay, consider when you reject on both side of the curve, then it is called as two-tailed test. Okay, it is called as two-tailed test. Okay, so this is called as two-tailed test when you have the rejection area on both the sides. Okay, with the equal percentage. Consider if it is 90 percentage level of confidence, say if it is 90 percentage level of confidence, okay, then what happens is your level of significance will be 10 percentage. Then what you say is you take 5 percentage on one side and 5 percentage on other side, then it becomes two-tailed test. Okay. The same way, if you say that, sir, I want a rejection either on this side or rejection on this side, or either left or right, consider that you are choosing this side. Okay, then it is called as one-tailed test. Okay, then it is called as one-tailed test. How you choose between one-tailed test and two-tailed test is, it depends on how you formulate the hypothesis. Consider that you are talking about some relationships. Consider that you are using a relational type of an hypothesis. Most of the time we use only two-tailed test. Okay, it is two-tailed test. The example that I give here, deals only with one single variable, like deals with the population mean and a sample mean, where you can go for a one-tail test. So it depends on the variables that you use, and it depends on how much of a scope that particular rejections is required. You choose between one-tail test and two-tail test. So coming back here to the same example of what we say alternate and null hypothesis, you can just look onto the diagram. I choose between this. So what I say, I want to choose a two-tail test. Okay, so now I have the level of significance, okay, is 5 percentage. It means that the probability is 0.05. What does this 0.05 tells? It says that you are allowing some 5 percentage of error. Okay, so 5% of error in the sense, consider that finally you accept a null hypothesis. Okay, accept null hypothesis is now it is 95% accurate, and there might be a 5% error might be there. So it is an allowable error. The limit or the level of allowable error is what we call it as a level of significance. Okay, so here I'm trying to show you a two-tailed test. Okay, a two-tailed test where the rejection happens on both the sides. You can just look on to it. Okay, uh, the level of significance denoted by alpha is equal to 0.025. So what I do here is this side I have 2.5 percentage, and this side I have 2.5 percentage. Okay, so the rejection is on both the sides. The rejection is on both the sides. So this is a two-tailed test. Okay, so So this side is what we call it as a lower limit, as portrayed in the graph. And just look on to that, what is lower limit and what is the upper limit. So on the left side, if on the left tailed of the normal curve, we call it as a lower limit, and the other side is what we call it as an upper limit. Okay, so how this critical values are calculated? These are calculated based on the test that we use. Here we are using one sample t-test. So for one sample t-test, this is how calculated. You need not have to worry about all these calculations, because nowadays we use all statistical software which calculates and give you. What we need to understand is what is this 3.196? That is what. Okay, so we need to understand the values, not mugging up the formula, how the formula comes and all. Okay, so this is critical value calculation on the upper limit, how you calculate, and for the lower limit, how you calculate. Okay. So when you look onto that, so we have calculated the lower limit, and the upper limit is also calculated. So this is rejected. This is a rejection area. This is completely a rejection area, and this side and 3.6, and this is again a rejection area. So your hypothesis accepted at this level. So this complete area is where is that our hypothesis accepted, which we say that our hypothesis is mu is equal to 3.06. This is the red color area shows the acceptable region, and the blue color area says that it is a rejection area. So moving on to the next, the common thing. So earlier we have discussed on how the rejection area happens using a one sample t-test, and this is a generalized form. Okay, this is a generalized form of the thing. Okay, the generalized form of the graph where the rejection values are there. So when you look on here, when you look on to this, right? So I'll just okay. So as I explained you, this is the rejection area in the red color I'm drawing, and this is a rejection area. So this is based on the test that we use, and this is an example of a two-tailed test where the rejection happens on both end. Okay, and the next one is the non-rejection area, the region of non-rejection, which is we say that whether you accept or reject the null hypothesis on that. And the critical area is the whole thing, which includes your upper limit and lower limit. Okay, so that is how it goes. Okay, so here, as I already told you, this is alpha by 2 in the sense that level of significance 5% we said, and one side it is 0.025 and another side is 0.025. That is how it is done. The next one is what is this p value, the critical value. Okay, so with this critical value only we decide whether the null hypothesis can be accepted or rejected. Okay, so it says that the probability of obtaining a test statistics equal to or more extreme than the observed sample value. Okay, so then you say that H naught is acceptable. Okay, so here what is this observed value is your actual values. What are the values that you say, like no, you assume things, right? So that is what is observed value. So what is the rule? Okay, what is the decision rule that we have? It depends on the p-value. So nowadays, when we use how this p-value is calculated, it's based on the statistical tools. We have statistical softwares like using SPSS, or even you can use Python in this case, or programming. We have something called as Jamovi, the software. Jamovi is there. So using those softwares, the software automatically calculates. Consider for a one sample t-test or for a two sample t-test, it calculates and give you the p-value. Okay, so uh, so if the p-value, okay, if the significant value is less than 0.05, what is this 0.05? It talks about the probability of significance. Okay, it means that it is level of significance. This here the assumed level of significance is 5%. Okay, so 5% level of significance, we say that it is 0.05. Okay, if the p-value is less than 0.05, what we do is we reject the null hypothesis. So this is the decision rule. Okay. If the p-value or the significant value is more than 0.05, then what we do is we accept the null hypothesis. So this is what we need to have in our mind, because all the softwares gives you the output, but it is again the interpretations that we need to write and the results that we need to write. We need to have this common understanding. Okay, so that is what is decision rule. So just rejecting null hypothesis, what does it mean is that we say that the result is significant. Okay, the result is significant. If we are accepting null hypothesis, we say that result is not significant. So this is again another interpretation that we need to remember. So we say that if we are rejecting the null, when is that we are rejecting the null hypothesis? If the p-value, if the significant value is less than the level of confidence. Okay. So here we are putting 0.05. What is this 0.05 is? It is level of significance. Okay, so you can have it as it is level of significance. So have a clear understanding about the decision rule. Okay, if the p-value, okay, if the significant value is less than the level of significance. Okay, if it is less than the level of significance, then we say that we are rejecting the null hypothesis. Okay, if rejecting the null hypothesis automatically says that it is result is significant. Okay, the result is significant. Okay, so technically, like no, technically how it can be illustrated is it is illustrated technically like this. Okay, so at so what is this 1.96? No, when we have learned statistics, you might have seen this 1.96. It is a tabulate. We say the tabulated value, calculated value when we do it manually, right? So this is the tabulated value for Z or T, the same thing, no? It is what. So this is an no, illustrated diagram about how p-value is calculated and how a decision is taken. But nowadays, like no, this is a very old traditional. I just put this slide because we need to understand how from traditional to the application of technologies here in the statistics. So we need not have to worry about this, because this is what we do technically when we have no SPSS. So this is the output that we get. This is an example of and one sample t-test. When we do it using some statistical tools, you'll get this a table. Okay, you'll get this table. Okay, where there are certain values here. Okay, so here when you look onto this table, there is something called as a test value, which is the population mean, actually, which is population mean. Just for an example, you have put one table here. Okay, and these are all the content in that. So salary is one variable. Okay, what we are trying to do is the average salary is 200 or not. So that is our testing purpose here. And this is t value. This is degrees of freedom. DF is degrees of freedom and significant value. And you have mean difference and the confidence interval. We have seen like no lower level, lower limit, upper limit. So those things all will come. So how a decision is taken, it is very simple. It is taken based on the significant value. So here it is a two-tailed test. The decision is taken based on this value, which is 0.0136. Okay, so this is the significant value, which we initially call it as a p-value. Okay, so the p-value is 0.06, which says that it is less than 0.05. What is this 0.05? We are testing the significant level at 5% level. So we are putting the value as 0.05. Okay, so if the p-value is less than 0.05, then we say that H naught is rejected. Okay, so the H naught is rejected. So what we say, the result is significant. So that is how a decision is taken. So it is very simple. We need not have to worry about any calculations and other things nowadays. We just look onto the output table, which is thrown by any statistical software that we use. And based on that, we should have the knowledge. It is enough that we have a knowledge related to how we are accepting or rejecting the algorithm. This part that we need to know. Okay. So you need not worry about how this values comes and other things, that all we are not, we need not have to worry. We need to have some knowledge on this, how at what condition H naught will be rejected, at what condition H naught will be accepted, and how to write the inference or interpretation. Okay, so that is what is this. Okay, so this is one example of how the decision rule is taken. Right. So hope the things are clear. I'll give you 2 or 3 minutes break. If you have any doubts related to what we have seen till now, you can put that in the chat box, and we'll be able to clarify. By the time we can also have some questions, and type in the chat box, we'll be able to understand whether all are there, or just devices are alone on. Okay. You can put in the chat box and we will be able to understand. By the time we can also have some polling now. It's really good to see many people are answering the question. We are able to see many people are answering. Very good. We are happy that we feel that we are not talking only to electronic device. We have participants, very active participants on the other side also. We are happy that more than 60% of the participants are very active. Thank you so much. Uh, and see the results. So the next topic of our discussion is this, which deals with parametric versus non-parametric test. Okay. So things are very simple. Like, when we assume that the probability distribution is normal, which follows a normal curve, or which shows that the trend of the data is normally distributed, which follows a normal curve, then we can blindly go in for a parametric test. When it is not normally distributed, okay, when there is no normal distribution, and you cannot make any assumptions, okay, related to the population. But when we look on to parametric test, we can have and assumptions. We can easily make some assumptions or prejudicial about the nature of sample or the population. But it is very difficult in certain conditions. It is not possible for us to have to assume what kind of a behavior that people will tend towards a particular thing or an object or for a particular event. Then it's better that we can go in for a non-parametric test. So based on the population distribution, we decide between whether it is parametric or non-parametric. So to get more insights into the difference, how it can be chosen between parametric or non-parametric. So as I've already told you, related to distribution for a parametric test, it is normal. And for non-parametric, it is not specific that it will follow a chi-square distribution, or it will follow a F distribution, or it will follow a binomial distribution. We cannot assume anything. Okay. In non-parametric test. And when you look on to the central tendency, what could be the midpoint? So we will not have a midpoint in non-parametric test. So we have only median, and you have an average. You will have definitely have a midpoint in parametric test. Okay, so that is how. And when you look onto the scales, how the scaling measurement levels, we can have an interval or a ratio scale when we use a parametric test. For a non-parametric test, it is just a nominal or an ordinal. So when we use an ordinal or a nominal scale of measurement for a variable measurement, then we can have an prejudice knowledge that non-parametric test can be used here. Okay, so this is a complete structure. Okay, so when we look on to the hypothesis testing, this is a complete picture about what are various parametric tests and what are various non-parametric tests. So it depends on the samples that we have. Consider that we have parametric and non-parametric test. So when we have one sample, when we work with one sample, then we can say that two tests are possible, which is t test or a z test. So when is this t test is used? T test is used when your sample size is less than 30. So when you have the sample size is less than 30, then we go in for a t test. If it is more than 30, okay, then we choose z test. Okay, so that is so t test is for we call it as a student's t test, which is normally for small samples, and z test is normally for a large samples. We can say that it is for small samples, and z test is for large samples. Again, the same thing when we have two samples, then we can have independent sample t-test or paired sample t-test. So when we have two samples, then it is again a t-test. where you can use here. It is also called as, when you look onto one sample here, we call it as a one sample t test. Here we call it as a one sample z test. And here, if it is two sample, we can call it as a independent sample t test or paired sample t test. Okay, so that is how it goes. Paired t test or the two sample or two groups t test. So this is about the parametric test. So it is completely about Z test and T test we use mostly in parametric. So other parametric, non-parametric tests, again, we have one sample or two sample. Here chi-square can be used, Kolmogorov and Simronov test, Rand's test, binomial test. All these things are for one sample each test. And when you have two samples, we have independent samples. Again, it is for now we have for independent sample test. We have chi-square test, Mann-Whitney U test, median test, Kolmogorov test. Again, when you have paired samples, we have sign test, Wilcox test, McNair test, and chi-square test. Okay, so these are all various tests that is possible based on the samples, based on whether it is one sample or two sample. When we use a non-parameters, we say that we cannot assume anything about the samples or the population. We are not unable to assume things might be related to the trend, related to the behavior, how does the data, whether they have any kind of a pattern. If you are not able to judge, then non-parameter test is used. And consider that you say that, sir, it does not follow a normal curve. Okay, it does not have a normal distribution. Then we go in for a non-parametric test. So again, based on whether it is only whether you're dealing with only one sample or whether you are dealing with two samples, okay, then we call it as then you go in for non-parametric test. It is based on, so here we have lot of choices of what are the tests that I can use, which what are the tests that I can particularly use. Okay, so this is about parametric and non-parametric test. So again, sir, do we have an equivalent test? Okay, so you say that no, sir, I am using one sample t test. Whether I have an equivalent non-parametric test? Yes, of course. So this is the table that shows what are the difference, what are the different possible things that I have. So this is how it goes. You can just look on two things. First one, for independent sample t test, we have Mann-Whitney U test. Okay, Mann-Whitney test is there, which is very equivalent. Okay, which is equivalent to it. The next one, you have paired sample t test, which is also called as two sample test. Two sample t test. We have Wilcox and sign rank test. So in parametric test, we have analysis of variance. Okay, one way analysis of variance. Here we have Kruskal-Wallis test in non-parameter, which is very equivalent. Okay, very simple. Like when you feel that it is a normally when a data you have no, when it follows a normal distribution, you go in for this and you say that, sir, I cannot make any assumption out of the data, then I go for a Kruse-Wallis test. That's the thing, that how you choose between parametric and non-parametric test. So we have one-way repeated measures of variance, and you have Friedman's ANOVA here in non-parametric, which is very equivalent to it. And the correlation, consider that you have Call-Pearson correlation, which comes under parametric test, and we have Spearman's rank correlation. So basically, when you look onto all this test, okay, when you look onto all this test, the parametric test mostly deals with metric variable. This is our key takeaway here. Okay, so parametric test mostly deals with metric variables, metric data, completely about the metric data. We have a metric data and all these things. And here mostly it is categorical. When you look onto that, it is completely a categorical related data. You have all the states that is applicable. Okay, so this is very simple. So the next, coming to the next point of our discussion about what is descriptive statistics and inferential statistics. Okay, So because when we choose between a bivariate or a multivariate or a univariate, it depends on what kind of analysis that we do. Here we have descriptive statistics and inferential statistics. What is this descriptive statistics? Okay, so it just describes the data. That's it. It completely gives a described data. How many people are there? What is the mean score? What could be the standard deviation? Okay, what could be the other value? Can I have any kind of further information? I will not have, because it just gives what is there. That's it. An average, a ranking you can put. So that is what. But what happens to inferential statistics is this helps you to draw conclusions. This helps you to draw conclusion, helps the people to make any decision related to the population under study. Okay, so this is no which has a practical implication. Okay, so whether this inferential statistics alone is very important, no. Without describing the data, without describing what it is, we cannot go in for inferential statistics. So we initially start with descriptive statistics to understand the nature of population. Then we move on to inferential statistics, which helps us to make certain decisions related to the sample or the population under study. And more importantly, this inferential statistics helps us to make decision. So it helps in decision making, which helps in decision making. Inferential statistics helps in making any kind of a decision, and so it has an applicability in it. Okay, so that is how it is done. This all I am rushing out because this again describes the same thing. The next one is inferential statistics. So example, like estimate the population mean weight using a sample mean weight. Okay. Estimation for hypothesis testing, test the claim that the population mean weight is 75. So I will be able to draw the conclusion about a using a small set of samples to a large set. So I can draw a conclusion related to a large population also. That is how inferential statistics works. Okay. So again, the next point of discussion is related to what are the tools that we usually use. Okay, what are the tools that we usually use and how does we deal with things. Okay, so these are all the tools that we usually use. Most of them, or parametric test we have. So we have t-test, that is students t-test, chi-square test, ANOVA, correlation, a linear regression, and multiple regression. I think during the last session there was some orientation given about chi-square test and ANOVA. Okay, so we will discuss on what are the types of test. Okay, for t-test we'll first discuss on t-test. Just a minute. Arjun, there is again the three questions are there. You can answer it up based on what we just discussed now. So we have two questions. Okay, question one and question two. First question is what is the region of rejection in hypothesis testing? We have different options. And second question is in hypothesis testing, what is the confidence level complementary to what it is equivalent to? We are able to see the people are actively participating in the poll. 33, 34 percentage, 36 percentage of the respondents are participating. By the poll, result share பண்ணணும். right? So thank you for your participation in poll, and we'll just look on to each test which are commonly used. Okay, so the first one is t-test. Under t-test, we have three kinds. One is one sample t-test, independent sample t-test, and paired t-test. Okay, so what is where does we use this one sample t-test? So all the way we were using only this one sample t-test. For an example, like no, so this compares the mean score of a known to an unknown value. Okay, so this which example like no sharing comparing the sample mean with the population mean. So when you are going to compare the sample mean with the population mean, one sample t-test can be used. So here we have only one variable, and that variable should be metric. Then only we can use one sample t-test. And for each test, now we have prefixed the the statements like the hypothesis, how a hypothesis should be for one sample t-test, for all the t-tests as such, right? So we need to have a statement like this. There is no significant difference. Okay, that is the protocol of using this t-test. We always use there is no significant difference. Here we are comparing the sample mean with population mean. So here the null hypothesis goes like this. There is no significant difference between the sample mean and population mean. Okay, so we know that alternate hypothesis is just opposite to null hypothesis, which says that there is significant difference between sample mean and population mean. Okay, so that is how it compares. There is a significant difference, and there is no significant difference. Okay, that is all. So this is one sample t-test where we have only one metric variable, and we are comparing one mean with the another mean. So mostly this population mean is an assumed mean. We don't have, but we assume that the mean could be like this. Okay, so that is what is one sample t-test. So for an example, I have put here a sample of 400 male student is found to have a mean height of some inches. Can it be reasonably regarded as a sample from a large population with a mean height of 66.39? So we have a 400 samples which is drawn from a population. So they are asking us to prove whether the sample comes from the same population. Okay, so we here have the null hypothesis mu is equal to 66 because that is the assumed mean, which is the population mean, which is an assumed mean. Alternate hypothesis goes which is not equivalent to 66.39. Okay, so the next one is independent sample t-test. Okay, so in a independent, typically this independent sample t-test compares two samples or two groups. Okay, two samples or two groups. So these two samples, what we are trying to prove here is whether these two groups, whether these two population, two samples, I'm sorry, whether these two samples comes from the same population or not. Okay, so that is what we are trying to prove here, whether these two samples under study comes from the same population or not. So statistically, what is the requirement here is, so we have two variables here. Okay, we should have some two variables. One variable is metric and another variable is categorical. Okay, one variable is metric and another variable is categorical. Okay, so with this combination of one variable and the no, two variables, I mean one is metric and another is categorical, we can go in for a independent sample t-test. Okay, so here again there is a constraint in this categorical variable. Okay, so what is a constraint here in this categorical variable is this categorical variable should have only two groups. Okay, this should have only two groups or two category alone. So one is metric, another one is category, which should have two categories. Okay, typically in the questionnaire, okay, typically in the questionnaire you have a categorical type of a question where you need to have only two options. Okay, and another one is metric, then I can go in for a independent sample details. So typically what I do is I compare two groups. I compare two groups with the same size. Okay, two groups with the same size, which says that whether the both group are significantly different or same. Okay, so that is how it is used. Okay, so there is no significant difference between the two means, or the mean of the two groups are not significantly different. So what is my assumption is both are same. Okay, that is how I mean here. Both are same. That is how this null hypothesis is formulated. What is the alternate hypothesis? It's just opposite null hypothesis, which says that there is a difference. Okay, there is a difference between two means. For an example, okay, so you have a sample of male and female related to shopping expenses. Okay, related to shopping expenses. You try to identify whether a female makes more expenses in shopping, spends more money on shopping, or a male spends more money on shopping. Then I can use this independent sample t-test. So I have two groups. Okay, one is category. I said, what is category? Gender. I say gender. So gender, male and female, you have two groups, and another one is metric variable, which is the amount that you spend shopping expenses. Okay, so this is a metric variable, or this is in terms of money that you measure, and you have two groups here, two categories, which is gender. Okay, gender, we have two groups. What is the two groups? Category variable is gender, which you have two groups, which is male and female. So two things are there. Okay, so this when you have the variables conditions like this, then I can use this independent sample t-test. So for using independent sample t-test, I need to have two groups, two group category variable and one metric variable. So how does I assume things here? I say that there is no significant difference male and female related to shopping expense. What does it mean is both male and female equally spends on shopping. That is my assumption. But basically, when you calculate, in the real world, it is not possible. For our hypothesis, we assume that male and female have make same kind of expenses. Okay, so for this we can use an independent sample t-test. Okay, the other kind of a t-test is paired t-test. Paired t-test. Okay, simple thing is both are metric. So you need to have two variables and both are metric. Sir, where does I use this paired t-test? Okay, so consider that you have a population. Okay, consider that it is a class that students are there. You go and teach vigorously, right? So it is consider that it is something like a remedial class. Okay, so because you take this extra thing, I mean extra care about our students, saying that they need to definitely get good marks in their end semester exams or university exams, and you go do vigorous teaching with them. Okay, and at one point of a time you feel whether my after the results, whether the result is good or bad, whether it has improved or not. But no, you have a question in your mind: how was my teaching? Okay, how was my teaching? Whether the teaching was really good or it was an average, whether it was useful to the students. I'm very much interested to know about it. Then what I do? Okay, in that point of a time, I can use this paired t-test. Okay, so you take the exam marks before you teach, before this remedial classes or some vigorous training is given. Okay, you have the marks or you have some scores before no, the training is given. Okay, so after you give the training to the students, after the vigorous training is given, after all the remedial classes are given, you keep a test and find the marks. Okay, so now we have the same variable mark. Okay, one is before training and another one is after training. This helps us to find whether our no our training was efficient or not. In those conditions, I can definitely use this paired t-test. So before a pre-experiment and post-experiment. So before that training is given, after the training is given, I'll be able to understand. Okay, I'll be able to measure the effectiveness of training that I've given to the students. In that condition, I can use this paired t-test. So what is my assumption here? My assumption here is now both are same. I mean, like before and after an event is taken done, both are same. I mean, both the marks are same. That will be my initial assumption. If you are rejecting the null hypothesis, it shows really my training was good, my training was efficient. Okay, so that for those purposes, I can use a paired t-test. Okay, so yeah, the same example I have given, pre-test and post-test of a training. So in this condition, I can use a paired t-test. So under t-test, we have this three tests. We have one sample t-test, independent sample t-test, and paired t-test. All these tests we can use it for a small samples where the sample size is less than 30. The same three tests, no, when you have large samples and if you work on a population with related to proportions, then I go in for a z test. So that is how here a t test and z test are there. But typically statistician use for everything, because nowadays we are using softwares and other things where even for large samples also people are using this t test, and we are able to find the answers are not that much different from when you use z-test. Okay, so these are all the three types of t-test. Okay, we'll move on to the next test, which is chi-square test. Okay, so chi-square test. What is so much no important about chi-square test is you must have seen in the earlier table, we had a parametric test and non-parametric test. Okay, in that and non-parametric, I put that as chi-square test. Sometimes chi-square can also be a parametric test, of course. Okay, there are certain populations where we are able to assume things, okay, where you have variables which is categorical, then ultimately I'll go and use for chi-square test. Okay, so you can explore and find chi-square is one of the tests which can be used as both parametric and non-parametric. So what is the condition here is two variables are there, two variables is needed, and both the variables are categorical. Then I can go in for a chi-square test. Okay, this I think in the last class, Sir was talking about chi-square test. And another one is one-way ANOVA. When we look onto one-way ANOVA, again you have two variables, one is metric and another one is categorical. Here in the categorical, there is one limitation here. In categorical, okay, in categorical, you should have more than two categories. You should have more than two categories when you use for ANOVA. But when you go for independent sample t-test, there we have category. Again, the same combination only for uh, independent sample test, also the same combination. What is the difference between ANOVA and this independent sample t-test is here for ANOVA, I need to have more than two categories, more than two options in a question, more than two groups in that. But in independent sample t-test, we need to have a category which is of equal to two only. So you should have only two variables there in t-test. Okay, independent sample t-test, we need to have only two groups. Okay, but here in ANOVA, the same combination where metric, here it is metric, it is categorical, and you need to have more than two categories. Okay, so that is what is the difference between ANOVA and independent sample t-test. Okay, so this is where I can use ANOVA. We'll move on to the next test, which is correlation. See, earlier again, correlation is both both parametric test and non-parametric test. Okay. So under parametric test, if you are using correlation, this is a Call-Pearson correlation. Okay. Call-Pearson correlation we use for parametric test. For this, you need to have both the variables as metric. Okay, when we have both variables as metric, and if we are able to make some assumption out of the population, then I use Call-Pearson correlation. I use Call-Pearson correlation. Again, the hypothesis or alternate hypothesis talks about the relationship between two variables. Okay, here only it talks about the relationship. Earlier, what we have seen chi-square or ANOVA or any kind of a t-test, we never talked about the relationship. Okay, Only here in correlation and regression, we talk about the relationship between two variables. Okay, so this is what is correlation. So in correlation, when you have both metric, then I go in for Pearson correlation. Pearson correlation, where you have both metric are there. Consider that when you have both variable or categorical. Okay, when you have both variable or categorical, but even then you want to measure. Okay, even then you want to measure correlation, then you can go in for Spearman's rank correlation, which is a non-parametric test. Okay, which is a non-parametric. So I can go in for a Spearman's rank correlation. Okay, so again, this is one kind where when we generally talk about correlation, it can be it can be a parametric test or a non-parametric test. If it is a parametric test, then I use a call Pearson correlation. If it is a non-parametric test, I use a Spearman's rank correlation. Okay. The next in the sequence when we talk about a relationship is simple linear regression. Simple linear regression. Right, so the next one is simple linear regression. So this clearly talks about the relationship between two variables. So both the variables are metric. So technically one can be dependent or another one can be independent. Okay, so dependent variable is what we call it as predictor. Okay, which predicts the independent. I'm sorry, independent variable predicts the dependent variable. Okay, so independent variable are called as predictors, which helps us to find. Consider you have example I have for a simple linear regression, prediction of son height using father's height. Okay, here the dependent variable is son's height and father's height. So using no the father's height, I am predicting the dependent weight. So here independent variable is father's height, dependent variable is son's height. So I can able to predict what is the son's height. And again, another example, you have sales and discounts. Okay, so again, this discount is an independent variable. Sales is a dependent variable. This discount will be able to predict the sales. Okay, so why this is called a simple linear regression is we assume that the relationship is linear. Okay, the first one is the relationship is linear and one variable is dependent and another one is independent. So using the independent variable, I'm able to predict the dependent variable. Okay, so this is called as simple linear regression. Okay, so basically when you learn about this relationship between one independent variable and one dependent variable, one independent variable and another dependent variable. So how does this hypothesis goes for a simple linear regression is you say that there is no, again we are seeing that there is relationship between variables. The same thing we have seen in the correlation also. Or else you can talk about the model fit when you talk about regressions, we can talk about this model fit. Okay, so you can say that the model is fit for a hypothesis, and alternative hypothesis say that the model cannot be fit. Okay, so that is how it goes. Simple linear regression. So consider that I have more than one independent variable. Okay, I have many independent variable and only one dependent variable. Then I call that as multi linear regression. Again, this is multiple linear regression. You just look on to the equation here is y equal to a plus bx1 plus cx2 something like that. So this x1 x2 are independent. So where you have more than one independent variable and only one dependent variable. Okay, when you have this, but again the relationship is linear, again the hypothesis, all this remains linear. What is the difference is you will have more than one independent variable here. Only that is the thing. Clear? So this is multiple linear regression. So for an example, okay, for an example, we have here gold price as dependent variable. How we are going to predict the gold price through GDP, savings in percentage of GDP, inflation, real interest rate, GDP per capita, money supply, all these things are independent variable. Using this, I am predicting gold. Okay, I am predicting gold. So this is an example of how the things occurs. Okay, so this is one example of multiple linear regression. So what is a simple thing? What is the simple difference between a simple linear regression and multiple linear regression is very simple. So you have more than one independent variable in multiple linear regression and these things, and the equation is same. Y is equal to a plus bx here because you have only one independent variable in simple linear regression, but whereas in multiple linear regression you have many independent variable. Okay, so these are all the few commonly used statistical tools. Okay, so the last point of our discussion is how can we go in for test selection. Okay, so before this, I think we can go in for a poll again, so we can just look onto your response related to whatever we have discussed till now. Dear participants, parallelly today's attendance link and feedback link also it is posted. You can just fill it out parallelly. So coming to the last point of our discussion, how there are various combinations and how we choose the tools. Okay. So this is a table which tells clearly about um, how to choose statistical tools. Okay, so the first one, you look onto the first option that we have, variable one. So the combination goes like this. So we have variable one and variable two. Okay. So when we have category variable, both the variables are category, then I go for chi-square test. Okay, which can be parametric or non-parametric. That is our wish. Okay. The next one, the second combination. So you have one metric and another one is categorical. Okay. So in this one categorical variable, if we have only two groups or two categories inside, then I go in for ANOVA test. Okay. So the next one is when we have one metric variable one metric variable, and two category variables are there, then I go for a factorial ANOVA test. Right. The next one is you have one metric variable which is dependent, and you have one or more factor variables, or if you have one or more controlling things. Controlling variable might be related to extraneous variable and other things which you want to keep it constant for a particular time. Okay. Then we can go in for ANCOVA, analysis of covariance. Analysis of covariance. This test can be used. So if you have more dependent variable, so many dependent variable are there and many factor variable are there, then I can go in for MANOVA, multivariate analysis of variance. The fifth combination goes like this. So one variable is metric and another variable is categorical, which you have only two groups. Then I go in for an independent sample t-test. The next one, you have two variables. One is pre and post, which we have discussed here, like measuring the effectiveness of training, like that. Then you go in for a paired t-test. One variable is metric, another variable is a metric, but the metric repeated many times. Okay, the same variable is there, but repeated many times, which is very similar to the earlier test. Okay, which is similar to this, where you measure only after one point of time. But here, many times are done. Okay, that is the difference between this paired t-test and a repeated measure of an over. The next one is when both the things are metric, then I use correlation. What kind of a correlation I use when we have both metric? We use Call-Pearson correlation. Correct. We use Call-Pearson measure of correlation. So this is one combination of different variables. Okay. The other combinations, we'll just look onto other combinations also now. So you have one variable, variable 1 and variable 2. You have one metric variable, another metric variable, but one is dependent and another one is dependent. We have seen just now, which is simple linear regression, Consider you have both are metric, both the variables are metric, and one is dependent variable, and you have many independent variable, then I go in for regression. Okay. And if you have more than one metric variable and you group it based on the factors, okay, you want to you want to group all those variables and check how all these things about the sample distribution and the other things, then I call it as factor analysis. Then you can use a factor analysis. When you have one categorical variable which is dependent, and you have one metric variable which is independent. You have many independent metric variables. Then I can use a discriminant analysis. Okay. And the other one, you have a dependent one variable. Okay. Dependent is one variable within two groups and many independent variables. Then I use a binary logistic regression. Another combination is if it is more than one dependent variable, either a category or metric, more than one independent variable, either category or metric, then I go in for a canonical correlation. So here mostly it is it can be either a category or a metric. Here also category or metric, but here what is the thing is it is more than one, and here also it is more than one. So if there can be many dependent variable, there can be many independent variable, which can be any kind. Then I can use a canonical correlation. Okay. So to find out the combination of attributes for a particular products, then you can go in for a conjoint analysis. Take example, consider you want to introduce new cars. Okay, so you with the different features of a car, you can put it a design 1, design 2, design 3, and different combinations can be made. Based on that, you can choose which is most preferred car. Then it gets into the production. So for those kind, I can use a conjoint analysis. The next one is if you want to find the validity checking item, construct, or convergent, or divergent, all this validity checking, I can use this confirmatory factor analysis, CFA. Okay. And if you want to build a model with all dependent and independent, too many independent variable, and trying to find as many number of relationship as possible, then I go in for a structured equation model. Okay, we call it as SEM, structured equation model. Okay, so these are all the various combinations of groups. So what we need to have an understanding here is we need to understand the variables, what are different kinds of variables, what kind of a combination that we have for a particular research problem. Based on that, we can use the tool, whatever the tool that we are using. Okay, so this is about different variable combinations and other things. Okay, so thank you so much for patiently listening for more than 1 hour, 1.5 hours. I know that it's very difficult in the afternoon sessions. Thank you so much for your patient listening. If you have any queries, you can put in the chat box. We'll be able to answer you. Thank you so much.
Thank you, sir. Thank you so much. As we draw to the end of the sessions, I would like to thank each and every one of you for your active participation. A special thank to our esteemed speaker whose expertise and passion have truly made this FDP an enriching experience. Thank you so much, sir. Tomorrow is the last day. Kindly join. Thank you.